are surrounded by dark matter and dark energy, mysterious forces that permeate the universe and play a fundamental role in determining its evolution. Scientists can observe the effects of these cosmic enigmas, but as yet, they have found nothing.
Der Weltraum.
Space, an infinite vastness. But there's nothing in it. In a volume of about 13,000 by 13,000 by 13,000 kilometers, which is roughly the volume of the Earth, there's the mass equivalent of a small grain of sand. Not only that, when you examine this grain of sand, you find it consists of ghostly particles, particles that pass through everything without leaving a trace. And then there's dark energy. What exactly are dark matter and dark energy?
Around 13.8 billion years ago, our universe began with an explosion, the Big Bang. It was the birth of matter, space, and time, the beginning of everything. Astronomers estimate that the visible universe contains approximately 2 trillion galaxies, each comprising 100 billion stars. But despite this, the universe is eerily empty. Modern cosmology traces the universe back to its beginnings. They are in search of the blueprint for everything, and in doing so, look deep into the past.
What we see today is the end result of a lengthy development process. When we look out into space, we're always looking into the past, and the deeper we look, the further into the past we look too. We don't believe that different areas of the universe develop differently, but that generally speaking, the universe always appears roughly the same everywhere.
Astronomy is a voyage of discovery into the infinite, always at the limits of our imagination. After the Big Bang, stars, nebulae, galaxies, and ultimately planets and even life came into being. Researchers are increasingly able to recognize and understand the complex structures and interrelationships in the cosmos, and are learning ever more about the objects within it.
We have galaxies, galaxy clusters, and galaxy superclusters. These are absolutely enormous structures. And we have the stars in the galaxies. There's matter between the stars. And we have certain types of stars that are all different. The galaxies are different too, and we have exotic objects like black holes. So there's a whole zoo of different star types, galaxy types, and types of matter in between.
Our knowledge about the universe has increased exponentially in recent years. But what we can actually see or detect only makes up a fraction of everything there is. There must be much more out there that influences the universe and governs its evolution. A mystery that we cannot comprehend. Large amounts of matter and energy that have yet to be proven by any scientist. Dark matter and dark energy.
What's really intriguing is that experiments indicate that we've only actually seen roughly 5% of our universe. The universe consists of 5% matter that we see all around us, roughly 25% so-called dark matter. That is, matter we can't see. And then a further roughly 70% of stuff that physicists don't have a clue about what it could even be. So they gave it a spectacular name, dark energy.
Dark energy and dark matter. Concepts that ultimately reflect the current state of scientific knowledge. Astronomers notice the effects these mysterious forces have, but are otherwise in the dark.
Da stimmt irgendetwas nicht.
Something doesn't add up.
Das führt man auf
And that leads us back to a gravitational effect.
zurück.
And we say it's due to dark
Sagt man, das ist die
matter.
dunkle Materie.
When we consider that there was a Big Bang, And since the Big Bang, the universe has been flying apart. Then you quickly come to the realization without further calculation that this expansion ought to slow down due to gravitational attraction. But it isn't. It's accelerating. So we introduce the concept of dark energy that causes the universe to expand. They're both just concepts that say, we have no idea.
Dark matter and dark energy seem to be ubiquitous and permeate everything. They are among the biggest mysteries in our universe.
A grain of sand within a region of space the size of the entire Earth. If you were to examine 6 of these grains of sand, you'd discover that 5 of them have very strange properties. They're basically invisible, which is why we call them dark matter. This dark matter, nonetheless, has a considerable influence on our universe, as it slows its expansion. And because we can measure this slowing very well, we can accurately determine the amount of dark matter there must be. Could it be that this dark matter is composed of black holes? That's a good question. It could be that there are many, many, many black holes finely dispersed throughout the universe. In order to answer this question, however, we first have to understand these black holes better. And it would help us to do so if we could obtain an image of a black hole. And this is exactly what scientists succeeded in doing in 2019.
It's an historic picture that astronomers presented in April 2019. For the first time ever, a global network of radio telescopes photographed the silhouette of a black hole. Black holes are the most compact form of matter we know of. Gravitational monsters that devour everything around them. Not even light can escape from them.
It was an amazing moment. It's an extremely difficult job. You can't see a black hole because it swallows all the light. But if you have a black hole here, and you're here, and on the other side there's a bright star, the rays of light from this bright star get bent around the black hole. And because it's here, a bit arrives everywhere. All of a sudden, you see a ring of light surrounding the black hole. And we actually found this. It's moments like these that, if you have a bit of feeling for such things, really make your heart sing and you say, black holes, they're not made up, they really exist.
No single telescope, neither in space nor on Earth, would be powerful enough to capture such an image. So, the scientists used a trick.
For an image like this, you need a telescope the size of the Earth. If you want a telescope that's as big as the Earth, you make it from separate telescopes that together act like a single telescope. All of the individual images are then processed to create a single sharp image using interferometry.
The Global Telescope Network created an enormous virtual instrument, the Event Horizon Telescope. It doesn't work in the visible spectrum, but captures radio waves. It's colored red so that it can be seen by the human eye. The black hole being observed is 6.5 billion solar masses and is at the center of the Messier 87 galaxy in the Virgo constellation, 55 million light-years from Earth.
We find black holes so fascinating because inside black holes, physics more or less stops working. Time basically comes to a standstill inside black holes. If you were passing by a black hole, you couldn't see into it, and we don't know what goes on inside them. That's what makes black holes so interesting. I think black holes became popular thanks to sci-fi films that depict how when something falls into them, it gets ripped apart and everything gets destroyed. It's actually correct in a certain sense because gravity is so strong inside black holes that ultimately everything gets obliterated.
There are countless black holes in our galaxy too. The largest by far is at the center of the Milky Way, 26,000 light-years from Earth. Sagittarius A star, a supermassive black hole of around 4 million solar masses.
The main thing a black hole does is attract other stars and bodies. It's an enormous mass that exerts a large attractive force on everything. So the assumption was that if you look carefully, you should see objects orbiting the black hole at high speed. The same way you can determine the mass of the Sun from the motion of the Earth, you can determine the mass of the black hole from the motion of the stars orbiting it. That's why we started measuring the trajectories of the stars close to the black hole very precisely.
Sagittarius A star is actually rather unremarkable, but now and then we observe sudden spikes in brightness. This happens whenever matter falls into the black hole. The Chandra X-ray telescope detects these outbursts too. Chandra first observed Sagittarius A star in action and saw the black hole devour matter at the beginning of the 2000s. Sagittarius A star is a valuable source for astronomers studying the conditions in the vicinity of a black hole. In May 2019, scientists detect an extremely bright flare-up. Sagittarius A star suddenly lights up twice as intensely as usual. The black hole in the center of our galaxy had apparently grown hungry. The flare-up happens on the event horizon of the black hole, the boundary beyond which matter and energy irrevocably fall into the gravitational abyss. Beyond this threshold, nothing can ever escape.
We, of course, asked ourselves, what was that? What did we just observe? Something must have fallen in, or the black hole wouldn't have emitted light. They gain gravitational energy, and this is released as radiation, and that's the flash we see. But what was it exactly? Maybe it was a rogue planet that was traveling alone and fell in, or a small gas cloud. As the light emission wasn't that big, it must have been a compact body that fell in quickly.
The observed event actually took place in the distant past, 26,000 years ago. That's how long it takes the light from the center of our galaxy to reach us. But there are other black holes quite near to our planet. In the spring of 2020, scientists at the European Southern Observatory detected one, approximately 1,000 light-years from Earth. 1,000 light-years. On a cosmic scale, this black hole is right next door to us. It's a so-called stellar black hole in the star system HR 6819, and only about 5 solar masses in weight. Together with 2 stars, it forms a triple star system. Small black holes like this are created when a star nearing the end of its life explodes as a supernova. The outer shell of the star is ejected, and the core collapses in on itself to form a black hole.
1,000 light years isn't very much, but this black hole is very docile. That is, it doesn't attract matter because there's none around. There's no gas in the vicinity. The stars are far enough away that they don't get ripped apart. And as long as it stays that way, the situation there will remain stable, and we'll have nothing to fear.
April 2018. A SpaceX Falcon 9 rocket lifts off, heading for Earth orbit. On board, NASA's TESS space telescope. TESS's actual job is to find exoplanets. To do this, it systematically scans the night sky. The telescope also observes a galaxy in which an unusual brightness distribution was detected. With the help of TESS, the researchers were able to observe almost from start to finish a star being torn apart and devoured by a black hole. Such a stellar death is very rare. The observed event played out around the supermassive black hole in the center of a galaxy in the Volans constellation, about 375 million light-years from Earth. Once the star enters the gravitational pull of the supermassive black hole, its fate is sealed. It was approximately the size of our Sun. The gravitational attraction of the massive object deflects the star from its trajectory and subjects it to enormous tidal forces as it nears the event horizon. These eventually tear it apart.
It heats up unbelievably. The star is turned into a disk that lights up extremely brightly, and when it lights up, it loses energy and moves ever nearer to the black hole until all of a sudden it's gone.
Black holes, gravitational monsters that devour everything in their vicinity. Not even light can escape from them. For a long time, they were purely theoretical. But nowadays, we can observe them and are learning ever more about these invisible concentrations of gravity. Black holes are simultaneously one of the dark secrets and most fascinating objects in our universe. Anything that gets too close to them is inevitably doomed and no longer of this world. Not even light can escape from them. Proving that they really exist was a landmark in astrophysics. Scientists speculate that there's a totally different mystery in the outer regions of our solar system, an enigmatic ninth planet.
We've had super telescopes out there in space for decades now. The Hubble telescope, the Kepler telescope, that allow us to see even small planets in distant solar systems. And now these astronomers come along and claim there's a ninth planet in our solar system. Why do they think that? Well, they say there are objects out there beyond Pluto that move very strangely, but they can't see anything. And that's why some astronomers say, well, if we can't see anything, this ninth planet could be a small black hole.
We can see Mercury, Venus, and Mars with the naked eye from Earth, Jupiter and Saturn as well. And they move as we would expect them to. Uranus was discovered by William Herschel using a telescope, but its orbit was different than expected. This could be an indication of an as yet undiscovered mass in our solar system.
There are clever mathematicians that then take these discrepancies and make a prediction about where another planet would have to be. A troublemaker disturbing the orbit. They then looked closely and discovered Neptune. It was a tremendous success for observational astronomy, of course. So people said, since that worked so well, maybe we can continue doing the same thing. So they carefully scrutinized the orbit again and concluded it still wasn't right. Something else must be out there. And then they found Pluto. And now people are saying it still isn't right. Something else must be out there. Problem, though, is that the further out we go, the more slowly the planets move. And it takes more and more time before we can see the disturbances. This means that the uncertainties regarding where the next planets are get bigger and bigger the further away they are. So we haven't managed to track down another planet yet. We don't even know whether we're looking for one object or perhaps several. It's just speculation. But there are indications that the orbits aren't totally undisturbed. So some of my colleagues do believe there could be something there.
The object would have to be about 6 times the mass of Earth and be far outside the orbit of Neptune. Astronomers speculate that there's a cloud of debris here that encloses the solar system like a shell.
About where Pluto is located is where the Oort cloud begins, a large quantity of small clumps of matter that also move around the Sun. But we've only known about this cloud composed of many smaller objects since 1990. And it's because of these smaller objects that Pluto lost its planet status. It's possible, of course, that another, somewhat larger planet is hiding in this Oort cloud too.
Up until 2016, Pluto was known as the 9th planet in our solar system. But as more and more objects of a similar type were discovered, scientists reconsidered the planet definition. Pluto was demoted to the status of dwarf planet and has since then shared this status with 3 other objects. They are all so-called trans-Neptunian objects, a collection of innumerable pieces of debris beyond the orbit of Neptune. Many of these trans-Neptunian objects have orbits that are similarly aligned. This is unusual, and so we concluded there was a common unknown cause, Planet 9. It was an anomaly in the orbit of Uranus that led us to discover Neptune. But this method doesn't seem to be working this time around.
The disturbance of Uranus was so large that it was possible to predict relatively accurately how big and where the planet had to be, and it was discovered accordingly. Someone predicted it had to be there. A telescope was pointed in that direction, and sure enough, there it was. We can't do that this time, as the disturbances are so small that they might not even be real. So in this respect, we're still a bit in the dark, literally.
There's another theory that tries to explain the unusually similar alignment of some trans-Neptunian orbits. There could be a primordial black hole in our solar system. Stephen Hawking described such primordial black holes in the 1970s. In contrast to all other black holes, it is thought that countless numbers of these very small objects were formed shortly after the Big Bang.
It's a theory. We haven't found any yet. You can search for them by observing the light from distant stars and galaxies, for instance. If small black holes were to pass by, they would bend space-time. You'd see abrupt fluctuations in luminosity, peaks. But this hasn't been observed yet, so at the moment there's no evidence that they really exist. It's just one possibility of the hypothesis, nothing more.
A black hole orbiting in our solar system could explain the strange trajectories of some trans-Neptunian objects. After all, it's just a question of mass and its effect.
It's actually irrelevant whether you say planet or black hole. It's an object that exerts a gravitational force. A black hole exerts a gravitational force, and a planet would exert a gravitational force. It would be impossible to distinguish between the two. Maybe a black hole sounds better than planet. If you say black hole, you're sure to get people's attention. The fact is, you can't make any distinction between the two.
The hypothetical object is estimated to have approximately 6 Earth masses. A black hole like that would be tiny. It would have the diameter of a grapefruit.
Could
Planet 9 really be a black hole? Let's first take a step back and ask ourselves what evidence there is for a 9th planet. Well, say the astronomers out there beyond Pluto, there are 6 small objects whose elliptical orbits are similarly aligned. But the alignments of elliptical orbits are always random, so it could also be 6 coincidences. And I find it unwarranted to use such an extravagant explanation as black holes for an argument as weak as this. But astronomers continue to look for Planet 9 nonetheless. But if you ask me, they won't find much.
In our universe, we see the entirety of space and time, matter and energy, and in between, nothingness, seemingly empty. But we know from observations of stars in galaxies and galaxies in galaxy clusters that there must be far more mass present. which is affecting the motion of objects in space. You just can't see it. Scientists are searching for this missing mass, which they call dark matter, due to it being invisible. But physicists are uncertain as to what it could be composed of. The scientists can only detect the effects this missing mass has. Dark matter interacts through gravity. Stars and galaxies simply do not move in accordance with the gravitational forces of the matter that is visible to us, and thus demonstrable.
In order to understand this strange behavior of the universe, there has to be more mass out there that we cannot see. Therefore, dark matter. But this dark matter has some very strange properties that I would like to explain to you now using this. Let's pretend this pen is made of dark matter. What would this mean? It means that light couldn't interact with this matter. It couldn't be reflected, for example, so you wouldn't be able to see it. It isn't just light that can't interact with dark matter, though. Even normal matter like my hand is unable to interact with it. What does that mean? If I tried to grab this pen, it would pass through my hand. I couldn't grasp it at all. That's what dark matter means. And not only that, if this pen were made from tiny particles of dark matter, they would be spread throughout the cosmos. There would be vast numbers of tiny particles, billions each second, constantly passing through our bodies, and we wouldn't notice a thing. That's what dark matter means.
Our Earth orbits the Sun, apparently unaffected by dark matter. Dark matter is evenly distributed over the relatively short distances in our solar system. So the disturbances it causes come from all directions simultaneously. As such, it has no overall effect. It neither radiates nor reflects light. We can neither see it, nor does it affect us. But it must be there nonetheless. Scientists assume that dark matter, like visible matter, is a product of the Big Bang and only affects large structures, like galaxies.
The sun's motion is much too fast, so there has to be matter somewhere else. And further out in the galaxy, the situation gets worse still. There, the stars are moving even faster relative to the speed they ought to be moving at. And this additional speed can usually only be caused by a mass. But we don't see it. This is why it's called dark matter, because we don't even know where it is and how we ought to interpret this. It's a mystery. Something must exist in the neighborhood of the sun that makes up this dark matter, and we don't have a clue as to what it could be.
On the basis of measurements and calculations, scientists deduce what the mass of the dark matter in the universe must be and how it is distributed. Whether it consists of one type of particle or several different ones cannot be said with certainty.
In an astronomical sense, dark matter is like a bucket of coal. It's there, but you can't see it in the coal bunker when it's dark. And we're in a similar situation. There's some matter out there that we can't see and are trying to find. But it's eluding our best efforts. It's very peculiar and is commonly referred to as dark matter.
So, dark matter is basically massive elementary particles, or perhaps numerous primordial black holes that we cannot detect. But they're responsible for the motion of stars and galaxies not obeying the laws of physics.
There appears to be 5 times as much dark matter as visible matter, so we have to be colliding with it all the time. But that's not a problem, since dark matter interacts via gravity. It doesn't interact with us in any other way. Dark matter isn't charged, we can't feel it, and it doesn't exert any other force on us. As such, the forces that dark matter exerts on us are themselves weak.
The purpose of the German X-ray telescope eROSITA is to gather information about the structure of the cosmos and its evolution. It's generating a map of the X-ray sources in the universe. And it's hoped eROSITA will provide new insights into dark matter and dark energy. To this end, the telescope scans the entire sky, primarily surveying so-called galaxy clusters. Gigantic aggregations of thousands of individual galaxies that are bound together by the force of gravity. It's about understanding cosmic evolution and the interdependencies in our universe. Dark matter acts as an attractive force through gravity, whereas dark energy drives matter apart. Based on its observation of galaxy clusters, eROSITA should help scientists better understand the interplay between these two mysterious forces. The data will be used to create a map of the skies, an image of the universe and its evolution.
Dark matter can simply pass through us without causing any injury. X-rays can penetrate us too, but they would harm us. There are forms of radiation that can pass through us and are not harmful, though. Neutrinos, for example, are particles that pass through us without causing injury. And dark matter could be composed of particles that don't interact with us at all. They are incapable of interacting with our particles, so they can pass through us without causing harm.
We know nothing about the particles that dark matter must be composed of. Although it constitutes over 80% of the matter in the universe, we've not yet succeeded in directly detecting even a single particle of dark matter. But entire galaxy clusters must be filled and surrounded by dark matter. The galaxies within them rotate much too fast. Without the additional gravity, some of them would have long been scattered in all directions. Dark matter permeates the entire cosmos, but it only makes its presence felt through its gravitational interaction with normal matter.
Whether it consists of small elementary particles or large elementary particles or clumps of something, we don't know. There are even those who say it's black holes. That would be worse if there were that many black holes here with that much mass to cause the Earth to move so fast around the center of the Milky Way.
Dark matter leaves behind traces in the universe. That it's actually composed of massive particles is a basic assumption. If this assumption turns out to be incorrect, classical physics would have failed.
They're investigating something without even knowing what to look for. I mean, if you want to know how bright a light bulb is, you have a specific job. But if you say, I'm looking for something, but I don't know if it even exists, I just see the effect of something, you're in a rather difficult situation.
Da ist man schon ziemlich in einer schwierigen Situation.
An even greater puzzle in modern physics than dark matter is dark energy. It appears to steer the fate of our universe as a whole.
There's something out there, namely dark energy, that accounts for 70% of all the mass and energy in our universe. What on earth is it? What we do know about it is that it's finely dispersed throughout the universe. Not just in empty space, but everywhere, in every body, in my body, in your body. What we also know is that it's also called ground state energy. What does this mean? It's the energy of the overall state of the universe. And because there's nothing lower, it means you can't tap into the energy to power something. For instance, like a smartphone or a car. We also know that this dark energy has the effect of causing space to expand, like yeast causes dough to expand. Isn't that odd? And there are now several space missions to find out exactly what it is.
Dazu gibt es jetzt mehrere Weltraummissionen.
Like the Hubble Space Telescope before it, NASA's Nancy Grace Roman Telescope will provide us with brand new insights into the wonders of the universe. The telescope is named after cosmologist Nancy Roman. In the mid-1950s, she established the Space Astronomy Department at NASA. The main objective of the telescope that bears her name is to investigate the distribution of galaxies in the universe and collect important data about the mysterious dark energy that permeates the cosmos and apparently causes the universe to expand ever faster.
What we observe in the universe is essentially radiation that interacts with matter. That is, solid material, tables, chairs, coal, rock, gas, etc. And at some stage, it has to emit light, and we can see it. But we've discovered that there are other forms of energy and matter in the universe that we can't see. The universe expanded. Then this expansion slowed down, but now it's speeding up again. Why is that? It's thought to be caused by some form of energy that we can't see, dark energy. And it too contributes to the total composition of the universe. All things considered, matter only makes up a few % of the entire universe, most of which we cannot see.
The Sloan Digital Sky Survey, or SDSS project, was set up to survey the night skies. For over 2 decades, the detectors have been measuring the position and brightness of around 470 million celestial objects. The result is a 3-dimensional map of the universe, which also provides insights into the effects of dark energy. The results support the theory that dark energy is the driving force of our universe.
Dark energy is, in a sense, something used to explain a physical process. Dark energy is a bit like anti-gravity. We know that gravity attracts masses. It's attractive. We see that the universe is expanding, and in actual fact, this expansion is accelerating. So there must be something that drives masses apart too. That's what this dark energy is. We don't have a clue what it might be, so it was initially given the name dark energy. But we really don't have any idea what it is.
Richtig wissen, was das ist, tut man überhaupt nicht.
Europe is also working on a dark energy hunter. The space telescope, named after the mathematician Euclid of Alexandria, is intended to help us understand why the expansion of the universe is speeding up. The telescope that the scientists and technicians are working on will observe the heavens in the visible and infrared spectrums simultaneously. Euclid's objective is nothing less than studying the evolution of the universe over the past 10 billion years. Within 6 years, the telescope will map out an impressive 1 billion galaxies. Dark matter and dark energy have a significant influence on our universe. Whatever they may be, the structure of the universe and its evolution are clearly dominated by these mysterious sources of force. Scientists are searching for the as yet unknown elementary particles of which dark matter must consist. But they still haven't found any traces of these hypothetical building blocks.
Dunkle Energie, was ist das eigentlich?
Dark energy. What is it actually? It's a property of empty space, of the vacuum. I'm going to draw a piece of the vacuum represented by this box. Now here's the thing. In the last century, a physicist named Heisenberg showed, and we know that it's true, that in such a vacuum, pairs of antiparticles pop briefly into existence. Here, for example, a negatively charged electron and positively charged positron that mutually annihilate shortly thereafter. And this is happening everywhere. Negative and positive. Everywhere in the vacuum. So why do we need something like this? Because it allows us to understand how an electromagnetic wave, which consists of a positive electric field and a negative electric field, is able to propagate. This wave has a polarizing effect. It drives the two virtual particles apart. And so we understand the propagation of light in a vacuum to be nothing more than the polarization of these virtual particles. With that, we finally understood it. But we now know that we need these virtual particles to explain how the universe, how space is being driven apart, because virtual particles scatter apart.
Could the vacuum energy really be the enigmatic dark energy, and thus have a significant bearing on Einstein's cosmological constant and the evolution of the universe? A natural assumption that many scientists go along with. But there still isn't a convincing model that would give this assumption a solid foundation.
Den einzigen Erklärungsversuch, den es
The only attempt there has been to explain dark energy so far is on the basis that it could be the vacuum energy. This sounds like a contradiction, since vacuum is actually nothingness. How should it contain energy? Our current understanding is that in the vacuum, new particles are continually being created and annihilated. This happens so quickly that we're unable to observe it. So what we see as a vacuum is an average condition, which is the result of so-called virtual particles being constantly created and annihilated. And they have an energy, so you can assign an energy to the vacuum. And this vacuum energy could be the mysterious dark energy. But when you do the sums, however, you come to the conclusion that although it's a nice explanation, the numbers don't add up at all.
A whole new generation of detectors is being constructed in order to shed light on dark matter. Among other things, scientists are looking for WIMPs, the favored elementary particles that could make up dark matter. Weakly interacting massive particles. But so far, we haven't been able to prove their existence.
The term WIMP stands for weakly interacting massive particles. That is, large elementary particles with mass, but that we can't see. But that's hypothetical. CERN is currently investigating. There are research projects trying to confirm the existence of WIMPs. You would have to be able to detect them on account of their momentum. So, conservation of momentum is a huge topic, but we can't find them. CERN has launched a research program, but at the moment we still don't know what it is.
Researchers are taking various and sometimes contradictory approaches in their search for the mysterious particles of which dark matter is thought to consist. But so far, they haven't been able to find anything.
Physicists always come up with interesting names, like WIMPs. There are also MACHOs, massive astrophysical compact halo objects. These are just objects, such as planets, that don't orbit a star and are dark. They emit so little electromagnetic radiation that we can't see them. Or so-called brown dwarfs, that are almost stars but don't shine. There would have to be a great number of them that we don't see in our observations of the sky, but that contribute to dark matter.
Albert Einstein occupied himself with the question of how the universe behaves as a whole. When the great thinker formulated his field equations for general relativity, it was still believed that the universe was static. However, his equations were only able to describe this static state if an arbitrary constant was introduced, the cosmological constant. a number that made his theory correspond with the accepted reality. But when it was demonstrated that the universe was in fact expanding, Einstein rejected this constant again.
Einstein's cosmological constant. Which is it actually? In his equations, this cosmological constant had the effect of causing the universe to expand. And this is exactly what he needed at the time, because people believed that the universe would have to collapse due to the mass it contains. But they observed a static universe, so the cosmological constant was needed. A few years later, however, a certain Mr. Lemaitre and Mr. Hubble came along and said, "We can see that the universe is expanding." So Einstein says, "I'm an idiot. I didn't need this thing after all." The situation is very different today. Sure, we see that the universe is expanding, and so don't need a cosmological constant for that reason. But then in 2010, a certain Perlmutter comes along and says, "I can see that this expansion is accelerating. So I need a cosmological constant again." So today, Einstein has been proven right again. On the other hand, there are astronomers who doubt whether the expansion really is getting faster. They claim it's simply an observational error. And then there are some physicists that say dark matter isn't made up of mysterious particles. It must be something else. Does this mean cosmology today is in a crisis?
The general consensus is that this enigmatic dark energy, which accelerates the expansion of the universe, can be simply described by Einstein's cosmological constant. But there are doubts, too. Some scientists even want to revise Einstein's entire theory. Some researchers simply doubt the correctness of the measurements of the increasing expansion of the universe.
Measuring distance in space is a fundamental discipline in astronomy. If there's one thing that has been repeatedly verified over the centuries, it's distances. You can be wrong, of course. There's always a margin of error of 1% or 2%. But if we are fundamentally wrong about the distance to the galaxies, then we have a fundamental problem with the whole of cosmology too. And if something is fundamentally wrong there, I'd say we have a problem with space-time, because it's giving us false information. I don't think so personally. Einstein had been right up to now, and I believe that will remain the case in the future as well.
Einstein's theory is a theory of gravity of masses in the universe. We can see dark matter due to its gravitational effect on the motion of stars and galaxies, but it still remains a mystery to us. And not all scientists are convinced that the expansion of the universe is speeding up. The proposed cause would be a mysterious force, dark energy. Here, too, we currently only have hypotheses to draw on.
I personally believe that these distance measurements are all correct. That means that accelerated expansion is real. The cause is dark energy, and that in turn is virtual particles in empty space. The real problem is dark matter, because we've been looking for these elusive fundamental particles for decades and have still found nothing. And then there are the primordial black holes, a kind of baby black hole left over from the beginnings of our universe. But to be honest, that sounds rather obscure to me. So, will we at some point be able to resolve the problem of dark matter? I personally firmly believe we'll get there at some point in time. And until then, things will remain really exciting.
Dark matter and dark energy. Together they make up 95% of the universe, according to the scientists' theories. But they have yet to solve the puzzle. And so, the vast majority of our universe remains a mystery, hidden in the darkness of space.